Hi everybody, a very good evening to all of you. I hope this video sees you in very good health. So a quick recollection of what we did yesterday. Yesterday I spoke about metal cutting tools. So as a manufacturer, the first thing or the most biggest priority that you need to give is the type of cutting tool that you use. So you must make sure that your cutting tool is effective. How do you know it's effective? How do you select your cutting tool? So you must make sure that your cutting tool has high hardness, it's wear resistance, tidak mudah tumpul, has high toughness, low friction. What happens if your tool has got high friction? High friction will generate high heat and therefore it will wear off your tool very quickly. So you must make sure your tool has got low friction and a relatively favorable cost. So these 5 factors must be present when you select your cutting tool to make sure that you have an optimized cutting process during your manufacturing process. Okay, today we're going to look at cutting tool signatures. So I must remind you that the cutting tool that you use in your manufacturing lab, okay, during your manufacturing process lab, whether it was the lathe, drilling, your milling, all your cutting tools had some kind of tool geometry associated to it. What do I mean by tool geometry? Yeah. Okay, in your house, when you see your knife, your house kitchen knife, yeah, you use that same kitchen knife to cut a fruit, you use that same kitchen knife to cut your vegetables, you use that same kitchen knife to cut meat, yeah, but in reality, that does not happen to cutting tools in the industry. Each and every cutting tool is designed for a particular task. You cannot multitask a cutting tool. Why? Because if you look at the diagram in front of you, the cutting tool comes with several angles associated to it. Okay, so if you look at it, you have the nose or the main part of the cutting tool is the nose, and it is followed by the shank. Shank is the body of the cutting tool. What performs your cutting is the nose of your cutting tool. So if you look at the nose of the cutting tool, it comes with several angles. What are the major angles? Okay, you see there is back rake angle, side relief angle, side cutting edge angle, side rake angle, and cutting edge angle. So each and every angle here has got a function. Okay, so if you're going to cut iron, the angles will vary. Your back rake angle will be a specific angle. Your side relief angle would be a specific angle. So you cannot have the same cutting angle for every metal that you cut. So it is a lot more complicated in the industry as rather than what you think it is. Yeah. So each and every cutting tool is designed to cut a specific type or category of metal. Okay. So let's see what is the contribution of these cutting tool angles to the cutting process itself. Okay, so I would pick 3 major cutting tool signatures, yeah. So for the first one, side cutting edge angle. Side cutting edge angle, if you look at the slide here, is over here, yeah. Side cutting edge angle. So side cutting edge angle basically varies between 0 to 90 degrees. What does it determine? It determines the chip thickness that you are going to generate. So the higher the cutting angle, the larger the chip generated. And is your tool going to be stronger or weaker by that? The tool is going to be weaker. Why? Because the higher the cutting angle or the higher the SCEA angle, side cutting edge angle, meaning that the depth of cut is going to be greater. Therefore, it will generate much bigger chips. What happens when that happens? Yeah, your cutting tool will become blunt very quickly. Akan jadi tumpul. Okay, so if your cutting tool becomes blunt, your tool life will reduce, and that means your tool is going to have a short tool life. Yeah. So as always, I mentioned to you, material, there are 2 types. You have a ductile material, you have a brittle material. So your problem does not lie in ductile materials. What are ductile materials again? Ductile materials are soft materials, yeah. So cutting a ductile material, it really does not matter whether you use a 20 degree side cutting edge angle or 80 degree side cutting edge angle, because generally your material is soft. The problem comes in when you're dealing with brittle materials. So when you're dealing with brittle materials, your side cutting edge angle matters a lot. It varies between 0 to 90 degrees. Therefore, if you have a choice, would you use a 20-degree angle or an 18-degree angle to cut a brittle material? Okay, I think I would want to choose a much smaller angle, because the smaller the angle, the smaller the chip size of the chip generated, therefore the longer your tool life is going to be. So remember, side cutting edge angle varies between 0 to 90 degrees, and the smaller the angle, the smaller the chip or the thinner the chip generated, and therefore the tool has a longer life. Secondly, side relief angle. Okay, which is side relief angle? Okay, so if you look at the diagram here, this is your side relief angle. Yeah, this is your side relief angle. So you see, side relief angle basically separates your nose from the shank or the body of the cutting tool. If you do not have a side relief angle, your nose and shank would be one basic or one joint unit, and therefore during the cutting process, your shank may even go into the cutting material which you do not want. Yeah, it may cause tool breakage and it may break your material as well. So side relief angle basically segregates or separates the nose from the body of the cutting tool. You have another one more important angle here called back rake angle. What is back rake angle? Back rake angle, you have two types. You have the positive back rake angle and the negative back rake angle. So what is a positive back rake angle? Positive back rake angle over here, yeah, positive back rake angle means that when you cut, your chip is going to, the chip generated would move away. It will curl and curl and curl and move away from the cutting zone, which is preferred. So when you use coolant, coolant is going to wash away your your chips, and therefore your tool is safe. Whereas negative back rake angle is a situation where the chip is going to curl in and move towards the cutting zone, meaning that it's going to gather around the cutting zone. Remember, if it ever happens that way where the chip does not break, it just accumulates and accumulates and accumulates and move towards the cutting zone, meaning that the tool may actually get welded at very, very high temperatures. When the frictional force is very, very high, the chip may curl, unbreakable, and it may stick onto the tool. It is a very disastrous thing to happen. Why? If the chip sticks against the cutting tool, meaning that the chip has welded against the cutting tool and your tool will be permanently damaged. You cannot use that cutting tool again. So to prevent that from happening, positive back rake angle is meant for ductile materials, meaning that as you cut, the chip will curl away and move away from the cutting zone. Whereas negative back rake angle is specially designed for brittle materials. Why brittle materials? Because the material will break as you cut it. So as the material breaks, it will not accumulate in the cutting zone, and therefore there's very minimal chances for the chip to weld against the tool. Therefore your cutting tool is safe. Yeah. So please pay attention to these three specific angles. My very commonly asked final exam question. So make sure you know how to label a side cutting edge angle, a back rake angle, and a side rake angle. Okay, specifically, and make sure you know the functions of this angle. How does this angle actually contribute towards the cutting tool? Yeah. So the next topic, inserts. Okay, so previously we used cutting tool, yeah, but now the latest style is people tend to use inserts. What are inserts? Inserts are, if you see this is your cutting tool, yeah, this is your cutting tool. What happens when the cutting tool becomes, or the nose becomes blunt? Okay, you need to remove the cutting tool, go and resharpen the nose, and then you reattach it again to your tool holder, and then you do the machining process. But now, and the latest trend is people tend to use inserts instead of a full hole cutting tool, meaning that you have a cutting tool which is a dummy and you place an insert on the surface of the cutting tool. So what performs the cutting? The inserts perform the cutting. So basically there are two categories of inserts. You have the indexable inserts and the disposable inserts. Okay, so indexable inserts are high quality inserts normally meant for mass production, and the inserts can be resharpened over and over again and used over and over again. Yeah, so once the insert becomes blunt, you can remove the insert, sharpen it and reattach it rather than regrinding the whole tool all over again. Whereas disposable inserts are guna pakai, meaning that if you have already utilized that insert, you cannot reuse it again. Once it's blunt, you need to throw it away. So normally we would want to use indexable insert for a mass production where your production is in large amount. You're producing 1,000 parts, 500 parts. Yeah, you do not want to waste your money throwing inserts. Yeah, and disposable inserts are specially designed for small amount of production. Okay, if your production rate is 50 pieces, 30 pieces, or maximum 100 pieces, it's fine for you to use a disposable insert, because disposable inserts are much cheaper compared to indexable inserts. Yeah, so indexable inserts is specially designed for mass production. What's mass production again? Large amount of production where you're producing between 500 to 1,000 parts. Okay, and disposable inserts are specifically designed for small production. Okay, so you always wonder, yeah, in the manufacturing processes class, did you ever ask your instructor what is the cutting tool made of, right? So you should have asked, what is your cutting tool made of? What is your lathe cutting tool made of? What is your milling machine cutting tool made of? Yeah, so there are several materials that are used as a cutting tool material. If you see the list there given to you, you have cemented carbide, high-speed steel, high carbon steel, cast non-ferrous alloy, diamond, ceramic, cermet. Cermet is a mixture of ceramic and metal, cubic boron nitride. Okay, however, despite having a long list of materials, a very commonly used material in industry would be high-speed steel and cemented carbide. Why high-speed steel and cemented carbide? High-speed steel and cemented carbide both are very, very cheap, readily available, but that's not the point. The most important point is the fact that cemented carbide and high-speed steel are very compatible with a lot of cutting tool materials out there. That is a very important point. Why? Because you can use the same cutting tool to cut several materials. When I say compatibility is one, compatibility in terms of hardness meaning that when you use a cemented carbide or high-speed steel to cut these compatible materials, your cutting tool would not break. Number two, there would not be any chemical reactions between your cutting tool and material of cut. Very important, yeah. You do not want to alter your cutting material. Okay, you do not want to alter your material. If there is a chemical reaction, initially your material is aluminum, and after the cutting process at the region of cut, you will find that the material has transformed to aluminum oxide. Oh, that is disaster, because that is going to change the characteristics of your material. You want a cutting tool that is not chemically reactive, an inert cutting tool material, and both cemented carbide and high-speed steel possess those characteristics. However, if it's affordable, your most best compatible cutting tool would be diamond. A diamond cutting tool is going to be your best bet. Why? Diamond is the hardest cutting tool material or hardest material available. It's chemically inert. That means it will not react chemically, and it can cut all the materials including another diamond. Okay, so diamond is the best cutting tool material. However, because of cost, you wouldn't find it regularly used in a normal manufacturing industry. Okay, besides that, you see I've got so many other options which is readily or can be used as a cutting tool material. Okay, so like I mentioned to you previously, during a cutting process, material comes out in the form of a chip. So you have a continuous chip as you cut, especially when you're cutting a ductile material, you will generate a continuous chip. When you're cutting a brittle material, you will have a discontinuous or fragmented chip, meaning that your chip will break as you cut. Okay, a brittle material would be a segmented or a discontinuous chip. A ductile material would be a continuous long form chip. Okay, so these are commonly found chips, but the only type of chip that we want to avoid would be a built-up edge chip. What is a built-up edge chip? So if you recollect, in the last slide, I mentioned to you something about the chip. Okay, if you use a positive back rake angle, the chip is going to curl and move towards the cutting zone, and at some point, if it's not being controlled, what happens? The chip may weld against the cutting tool. Okay, so this happens especially if you're dealing with an overly ductile material. So that generally, as I mentioned to you, material, there is two types. You have a brittle material, you have a ductile material, right? So if you're dealing with a brittle material, no problem. If you're dealing with a ductile material, you have something micro there, a micro type of material called an overly ductile material. Overly ductile material is overly soft, yeah? So the material, as you cut, the chip would not break. It will keep curling, and at some point, it may weld against your tool. And once it welds against your tool will become damaged. You cannot use, it's not like paper sticking against to paper, yeah? It is metal sticking against metal, and it's going to be a permanent weld, and you cannot do anything about it. So in order to prevent that from happening, when you're dealing with an overly ductile material, you must make sure that your cutting tool has got a chip breaker. What is a chip breaker? A chip breaker is installed in your cutting tool to make sure that as you cut, the chip is having an obstacle. It's not going to be a smooth flow of chip, yeah? The chip is going to have an obstacle, and when there is an obstacle present, the chip will have to automatically fracture. Okay, how does that happen? Let me show you, yeah? Okay, so you have three types of chip breakers, okay? So chip breaker, okay, you have three types of chip breakers. You have the step type chip breaker, groove type chip breaker, and you have the braced chip breaker. Okay, so you have the step type, groove type, and the brace type. What is a step type chip breaker? Okay, so if you look at it, step type is when you have your cutting tool. Okay, so the chip would curl, move, and cut, and there's nothing to prevent it from having a smooth flow, yeah? So what you do is you're going to incorporate a obstacle in your cutting tool, meaning that for a step type chip breaker, this is your smooth cutting tool, and you're going to incorporate an obstacle where instead of having a super smooth flow, you are going to create an obstacle. You're going to remove this part of the cutting tool. So your cutting tool will look something like this. So when the material flows, and at this point, there is an obstacle, you're missing this point, right? So your chip would be forced to break. So there would not be a continuous flow of chip. Groove type also has an obstacle, but groove type obstacle occurs in the middle. So when the chip comes to this point, it will automatically break, yeah? Brace type is when you have an obstacle, or you actually add on an extra material on the surface, okay, to create a thicker surface on the on the edge, and therefore the material is forced to break when it arrives at this point. Okay, so a chip breaker is necessary when you're dealing with an overly ductile material to make sure that your chip breaks as you cut. Otherwise, you would have a chip welded against the tool and a tool damage. Yeah. Okay, coolants, I think you've seen or you've come across this term coolants many times in your life. Okay, especially in your previous semester when you dealt with manufacturing processes lab. Coolant is a very important liquid or fluid used during a cutting process. If I were to give you this in the final exam, it's a giveaway, yeah. Please specify 3 functions of coolant. So make sure you know at least 3 functions of coolant. Yeah, if you look at it, what's the application of coolant? To reduce the frictional force between chip, tool and workpiece, reduce the temperature of the work and the tool, to wash away chips, improve surface finish, reduce the power required, increase tool life, reduce possible corrosion, help prevent welding the chip to the tool. Okay, so that concludes the lecture today. Please go back, go through these slides, and at the end of this lecture, I would give you an assignment. Please do your assignment, hand it in to me. That will be counted towards your test marks, your quiz marks. Yeah. So as of today, I would like to end the lecture. Thank you and see you in the next lecture.